So we've already talked about arithmetic sequences in which a pattern is increasing by the same amount each time, like a linear function. Today we're going to talk about geometric sequences. And that's a sequence in which a pattern is repeating each time again, but this time it's by using multiplication. So a sequence is built by multiplication. And where we use D to indicate the common difference in an arithmetic sequence, we're going to use R to indicate the common ratio in our geometric sequence. So for example, we could say 3, 6, 12, 24, etc., in which our common ratio is 2. So we're multiplying by 2. That would be our geometric sequence. So we're going to find an expression for each sequence and then find the indicated value. And just like the arithmetic sequence, we could rely on a linear function. The geometric sequence, we're going to rely on an exponential function because we are showing multiplication. So I'm going to skip down to this general form. Any geometric sequence in which we are using that multiplication, we can write it as a sub n equals a1, so our first term, times r, so we're multiplying by r, n minus 1 times to get to the indicated term. So going back to this first problem, if I want to find a12, well, first I'm going to write my expression. So we will say an equals, first term was 2. We need to look at our sequence and determine what we're multiplying by to get from one term to the next. Hopefully you recognize it as 4. And then my exponent would be n minus 1. So this then would be, if I want to find a12, would be a1, so 2 times 4 to the 12 minus 1, which is some big old number that I'm going to let you go ahead and multiply out. So 2 times 4 to the 11, which equals, I don't know. How about the next one? Again, is this geometric? Are we multiplying by something? You might say, yeah, we're dividing by 2, but for geometric, we need to show it as multiplication. So instead of dividing by 2, let's show it as multiplying by a half. Okay, so a1 is 6, my r is a half, and then I would have my n minus 1 as my exponent. So if I want to find the 8th term, I would take that 6 times 1/2, 8 minus 1 times, which is 6 times a half to the 7th. And again, I'll let you finish up with the calculation. Okay, so there we have our general form, which again just shows our sequence as an exponential pattern. Okay, so let's go ahead and get to the problems where you have two specific terms and you want to find a different one, but we don't know R and we don't know our first term. Okay, so let's just plug in what we know. I'm going to take the biggest term I know and write that as AN. So I know A10, okay? So I'm going to say that, okay, A10 equals, now I don't know A1, but I know A4. So let's base it on the fourth term. So if I'm multiplying by R, and I want to get from the fourth term to the 10th term, they are 6 terms apart from each other. Okay, so I'm writing my 10th term in terms of my fourth, and then multiplying 6 times to get to the 10th. Now let's plug in the numbers. So A10 is 125 over 64. A4 is 125, and I'm multiplying by R 6 times. And now all I need to do is solve for R. Okay, so to solve for R, I'm going to divide over my 125. Now remember, dividing by something is the same as multiplying by 1 over it. Hey, look at that. 125s will cancel. So this leads me that R to the 6th is 1/64. And then I can do my 6th root of 1/64. So from that, I can say that R is a half. Okay, so I now know the fourth term, the 10th term, and I know what I'm multiplying by to get from one term to the next. Now let's kind of restart the problem, but build it the same way. I would like to find A14. I'm going to base it on one of the terms I already know. And it really doesn't matter which one. I typically pick the bigger one of the two. Again, doesn't matter. So A14 must be my 10th term times R how many times? If I want to go from the 10th to the 14th, should be 4 times. Okay, let's plug in A10. A10 was 125 over 64. Let's plug in R. R we just found was a half, but I need it to the 4th power. Okay, and I now have all the information I need to find A14. So 125 over 64 times 1/16. And then again, I'm going to let you do the math to figure out what that term is. So that's the process. Build on what you know and solve for what you're missing. Okay, what about sums? If I have a finite sequence, one that ends, I can find the sum of it. So Sn equals, it would be A1, so first term times 1 minus r to the n divided by 1 minus r. So you can see we need to know first term, we need to know our rate or our common ratio, and we need to know how many terms there are. What we don't need to know is that last term. Remember, we had to have that with arithmetic. Geometric, we don't need to know that. Okay, so I would like to find the sum of this sequence. I need to know the first term. I'm going to find the first term by plugging 1 in. So A1 equals 4 times 0.3 to the first, which is just 1.2. I need to know R. So what is it that we're multiplying by? Now, a couple ways we can do that. We could go ahead and find the second term to see what we're multiplying by. Let's see, what would that be? 0.3 to the second is 0.09. 4 times 0.09 is 3.6. No, 0.36. There we go. I'm going to get that decimal right. And then I could say, okay, what am I multiplying by? But the easiest way to do this is just to look at the pattern. This thing right here, that's your R, because that's what we are raising to the power each time. Okay, it will not work out that the first thing is always A1. You'll see that here. But the number that's being raised to the power is your R. Okay, so I'm just going to jump to that and say that R is, okay. I also need to know how many terms there are. So if this sum is going from 1 to 12, then I know that n is 12. Okay, so we can go ahead and say the sum of our 12 terms is A1, which we said was 1.2, 1 minus 0.3 to the 12th over 1 minus 0.3. And again, I will let you do the calculation from there. Okay, now geometric sequences are interesting too because you can actually find the sum of an infinite sequence. Now, not every infinite sequence has a sum, but there are some that do. So that's kind of an interesting change and something to think about. So in these, I'm going to say S for sum. There's no subscript because it's an infinite sequence, so no set number of terms. All we need for that is our first term, which we will then divide by 1 minus r. Now, the condition that's been set here, though, is that these only have a sum if the absolute value of your r, so the positive value of your r, is smaller than 1, which means we're multiplying by something less than 1. Our numbers are sequentially getting smaller and smaller and smaller, and eventually will turn into a number as close to 0 as you can get. Okay? Those are the only types of infinite series that have a sum. So I'm going to go ahead and find this. Now, first, I want to make sure that this infinite series, you can see it's infinite because the infinity, has a sum. So I need to check my R value. But remember, the R value is the guy that's being raised to the power. So as long as this number is smaller than 1, we can find our sum, which it is. So now sum equals A1. Haven't found A1 yet. Let's go ahead and plug in our bottom value. So 4 times 1/5 to the first. So 4/5. So A1 is 4/5. Divided by 1 minus r. We said r was a fifth. Okay, so it looks like we have 4/5 divided by 1 minus a fifth is 4/5. Looks like the sum of this thing is just going to be 1, which is an interesting notation. Interesting idea. Okay, so that's all we need to know about arithmetic and geometric sequences and series.